and then bring back through that path. We will say that this can be replaced by this closed path integral. And we know from the Stokes theorem that that is the integral of the curl of A. So that's the flux. Right? So that's the shift in the phase. Now, in order for that solenoid to be not observable, you have to have no shift in the pattern. Otherwise, you know that there is something there. Even if you can't see, there is something there, right? So, for this to be not observable, this has to be 2 n pi, right? So this is going to be 2 n pi I plus the original shift, but that's equal to the original shift because you have the I there. And this is the Dirac quantization condition. If you put this this equation there, plug that into that, you will get the Dirac quantization condition. Right. Okay. And so the next thing we're going to do is we're going to derive some properties of the magnetic charges when it moves. So if you recall, you know that the electric charges is a Lorentz scalar, namely it doesn't change, it doesn't depend with the motion of the charge. So we want that to be true as well for the magnetic monopole. Otherwise, even if you have this condition and you boost it, and if it's not Lorentz invariant, then you know that it's not a physical charge, right? So let's suppose that we are so lucky that the solenoid lies in this direction, which I'm going to take it to be the x prime direction. And then we have another frame, which is the xy direction. Now, this frame, where it's the rest frame for the solenoid, is moving with relative velocity u in the x direction. Now, if you transform the magnetic field, you see that the magnetic field in the x direction is the same. And that means that if you compute the flux through this cross-section, it's going to give the same flux, right? Because you have the same magnetic field. And this cross-section here doesn't have a length contraction effect because it's perpendicular to the relative velocity. So this means that you're going to get the same flux. And that means that our monopole, the charge, is Lorentz invariant. Now you might be worried that this is quite special. Is it like true in general? Turns out that it is. Because even if you have this solenoid lying in a funny direction like this, we just need to be a bit smarter and then say we're going to induce the flux through this cross section. So it's going to be perpendicular to the U. But then we know that this is true, and we know that this doesn't have a length contraction effect. So we know that it's going to give the same flux anyway. And then you might ask, is it going to give the same flux as this surface? And the answer is yes, because the magnetic field is lying along the direction of this solenoid. So there is no contribution from the surface there. And so we conclude that the magnetic charge is Lorentz invariant. So that's one thing. Now, if you remember, the electric charges, when it moves, it gives rise to magnetic field as well, right? And The same actually happened to the monopole. Namely, if you have a monopole and then you send it into a motion, it will give you the induced electric field as well. And it is because, so let's say that we adopt this same picture. If you do the Lorentz transformation, you wouldn't see that the electric field is that. Yeah. Yes. So this gamma here is gamma u. So this is just transformation of the F mu nu, and then you get this. So the B prime is the magnetic field in this X prime frame, and the E here is the electric field in this X frame. Now, if you recall the Biot-Savart law, you see that if U is very small, then we have that E is minus U cross B prime, which takes exactly the same form as the Biot-Savart law, because this is that. Right? Because in the Biot-Savart law, you just change this to electric charges and then change this to E field, and then you'll get the Biot-Savart law for the magnetic monopole. And well, I guess since I have time, I can show you actually one more thing which I think is cool, which is that let's do it again. If you compute the interaction between two magnetic monopoles, namely, let's suppose that you have one that, let's say the other one that, you would expect to have a Coulomb's law for this magnetic monopole, right? And, well, actually I'm not going to do the whole calculation, but let me just say that if you compute the interaction between these two magnetic monopole, because we know that the force acting on the monopole is that, right? And then you just take the monopole field from this solenoid, and then you just dot it with each dipole there, and then you sum it all up, then you get the force. And the other thing that you need to be careful is this is hitting, it's the differentiation with respect to the position of the monopole. So it's not the same along this solenoid, but then it's easy because this is minus dr, where r is this vector. If you go and calculate, you'll see that the differentiation with respect to this position is minus the differentiation with respect to that position. And then you get the same differentiation everywhere. So what you need to do is you just need to do this integral, and then you take the gradient. And what you will see is you indeed get the Coulomb's law for this this magnetic monopole. And actually one can go even further and derive the Lorentz force law for the magnetic monopole, which is Qm